In part 5 of the airfoil section of our aeronautical engineering course, we're going to look at how this resultant vector, this vector that results from having a vertical lift component and a horizontal drag component, we're going to look at how this resultant vector acts as this angle of attack changes. Okay, this angle of attack, we'll call it alpha. This is the relative wind that's coming this way. The wing is aimed that way, but it's going this way, straight and level. So we've got an angle of attack of alpha. We've got a lift component here, which is always perpendicular to the relative wind, not perpendicular to the chord, but perpendicular to the relative wind. We have a drag component, which is parallel to the relative wind. And we have a resultant vector which results from those two components. You just go draw a dotted line over there, the length of the drag vector, draw a dotted line up to there, the length of the lift vector, connect from there to there, and you have your resultant vector. We'll use the data from this Clark Y chart on page 5 to determine how this resultant vector acts. See, they give us the coefficient of lift there from negative 0.2 to 1.0. They give us the angle of attack from a negative 8.4 degree angle of attack to a positive 21.9. There's the coefficient of lift at any given angle of attack. There's the lift over drag ratio. If you take the number in this column, or this column, the coefficient of lift column, and divide it by the number in this coefficient of drag column, like that 1.0 divided by 0.0721, you'll get 13.9. This number divided by this number equals this number. So we're going to use that to determine how this resultant vector acts, how much its magnitude changes as angle of attack changes, how much it moves forward, and how much it leans forward. The reason we want to know all this is so we can keep our center of gravity in front of it. The lift has to always be behind the center of gravity so that the tail can push down on the plane to give the plane stability. We're going to call our angle of attack alpha. See, there's the Greek letter alpha. We'll call our angle between vertical and our resultant vector beta. And we'll call the angle between our chord and our resultant vector theta. Notice we use Greek letters to talk about angles that we don't know about. Perhaps that's where the expression, "this is all Greek to me," came from. But we're going to dig into this and we're going to find out what all these angles are. As you can see, this is the direction of the relative wind coming from here. From here to straight up, where the lift vector goes, is 90 degrees. From straight up over to the resultant vector, we'll call it beta. So the whole angle from there to there minus this angle will give us this angle theta. And that's what we're interested in, so we can keep that center of gravity forward of the resultant vector. Okay, on this page is information that was transcribed from the chart of the Clark Y airfoil, starting with a 0 degree angle of attack. I didn't look at the negative angles of attack, just looked at 0 through 21.9. Here are the coefficient of lift numbers. Here are the coefficient of drag numbers. Here's what you get when you divide each number in this column by each number in this column. 0.5 divided by 0.0230 will give you 21.7. 0.8 divided by 0.0483 will give you 16.6, and so on. This is lift over drag. Okay, this is our angle beta, the angle between the vertical and the resultant. We calculate this angle beta by using trigonometry. We know that this is a right triangle, this being our right angle, that being one of the acute angles, and this being the other. We know that this side is the opposite side of this angle beta. This side is the adjacent side of this angle beta. So if we refer to our buddy SOHCAHTOA, SOHCAHTOA, we can see that we can use the tangent function, which involves the opposite side and the adjacent side of a right triangle, to determine this angle. If we already knew this angle, we could just punch it into our calculator and hit the tan button, and it would tell us what that over that is. But that's not the case. We know what that over that is, and we don't know what that is. We know that for this first one, coefficient of drag would be 0.0175. And we know that would be the coefficient of lift, which is 0.4. But we could just take the reciprocal of our lift over drag, because the tangent of angle beta is equal to drag over lift. So if we take our 22.9 here, get the reciprocal of it, 22.9, then hit our 1 over x to see what 1 over 22.9 is. It's 0.043668122. Okay, so we've got the ratio of that to that. So if we hit our invert tan button, we'll see what our angle beta is. Invert tan, we get 2.500, long string of numbers. So let's just write 2.5 under our beta column. And if we do the same thing for these other ones, let's see, 0.5 is our coefficient of lift, divided by 0.0230 is our coefficient of drag, gives us a 21.7 lift to drag ratio. But we're interested in drag to lift, so we'll hit our 1 over x button, get the reciprocal of that, which is 0.046. Now we'll hit our invert tan button to see what angle that is, and it's 2.63374, blah blah blah. So we'll just call it 2.64 is what I wrote here. Yeah, because I used the 21.7 instead of dividing that by that. We just did that by that, which doesn't give you exactly 21.7, but we're in the ballpark. Okay, let's just use these numbers and we'll get these numbers as a result. 19.7 is our lift to drag ratio. Okay, hit our 1 over x button, we get 0.05076. Hit our invert tan, we see that it's 2.9 degrees, 2.905921, so we call it 2.91. Okay, we just keep doing that same thing on down the line. We write down all these numbers. They range from 2.5, they get bigger and bigger, 2.64, 2.91, 3, 4, 5, 6, 7, 10, 13, 17. This angle beta from the vertical keeps getting greater and greater as our angle of attack increases more and more. But what we're really interested in knowing is what our angle theta does. This Greek letter theta, this angle between the chord and the resultant vector. We can see, we know beta gets more and more as the angle of attack increases. But does theta get more and more as the angle of attack increases? No, it doesn't. We're about to find that out. We know that theta is equal to all of this minus this. Theta is equal to 90 degrees plus beta minus alpha. Theta equals 90 plus beta minus alpha. So let's just figure out what theta is. 90 plus beta, 92.5 minus alpha, which is 0, gives us a 92.5 angle for theta at our 0 degree angle of attack. And as we increase our angle of attack, 1.4 degree angle of attack, we'll see that theta is equal to 90 plus 2.64 minus 1.4, which is 91.24. And we just keep doing the same old thing on down the line. Here we go, 90 plus 3.16 minus 4.1 gives us 89.06. As you can see, these numbers, they start out at 92.5. It starts getting smaller. Okay, this angle theta starts out at a little more than 90 degrees, but yet it starts dipping forward and becomes less than 90 degrees and drops on down as low as 81.31 at the stall angle, at the angle that has the greatest lift of 1.325. And after that, our angle starts again to increase from 81.31 back up to 86 degrees at the maximum angle listed on this chart of 21.9 degrees. Okay, the data on the chart on page 5 tells us that at a 0 degree angle of attack, our center of pressure is at 42.5% of the way back from the leading edge to the trailing edge. And at the maximum angle of attack of, let's see, 14.7 degrees, okay, the center of pressure is at 30% of the way back from the leading edge to the trailing edge. And all the other intermediate angles of attack between 0 and max, it's somewhere between 42.5% of the way back and 30% of the way back. So as you can see, this is what our resultant vector looks like as our angle of attack increases. See, this is all one, it looks like one wing, but it's really this wing, this angle of attack, this angle of attack, a bunch of them in between. At a low angle of attack, it's like this arrow. The center of pressure is toward the back of the wing, and it's not very much lift. The coefficient of lift is small at a low angle of attack. At a higher angle of attack, the center of pressure moves a little bit forward and becomes greater. At the stall angle, it's as forward as it's going to be and maxed out as high as it's going to be. So as you can see, if you have a low wing airplane, here's your wing and the pilot and the engine and all the heavy things are up above the wing. The center of gravity is up above the wing. You can see that this vector starts to sneak up on the center of gravity more so than it would on the center of gravity of a high wing airplane, where the pilot and the engine and the wheels and all are down here. Well, obviously the wheels are down below the wing on a low wing or a high wing, but the center of gravity is down below the wing on a high wing airplane. So this change is much greater, and as you can see, the center of gravity on a low wing airplane has to be placed a little more forward than the center of gravity on a high wing airplane. In our next lesson, we'll talk about how much lift we get out of these wings.